we have done in the last semester. So coming to our introduction, so we know that humans have multiple mediums to perceive knowledge, each with unique features. So we want to kind of emulate this for multimodal, machine learning models. So the problem that we're trying to address is to add a new dimension to classical question answering system. We aim to build a robust question answering system that answers based on other parameters. Specifically, we consider visual question answering, but the system is expected to answer questions about an image. Here are a few examples of such types of questions that we got from one of our data sets. Okay, so the current limitations of our MQA models are so there are problems about inability to identify all objects in the image. There are limitations in terms of recognizing primitive relationship between objects. For example, if you see the second figure, the question is how many giraffes are drinking water. But to detect that particular giraffe, basically we need the relationship over there, right? So few models are not able to do that. And there's also need for improvement in terms of accounting-based questions like you see in the first image. Other than this, there are inability to answer questions based on external knowledge, like you see the images on the right regarding weather, climate science, and technology, etc. So we kind of want to build a machine learning model that can solve all these problems. So we divided our semester into sprints of 2 weeks each, and we focused on multiple milestones such as collating the different data sets, model training, evaluation, error analysis, constructing a data set that is used for the router model that joins all the models based on our class, which we'll be talking about in great detail in our presentation. Okay, so this is what we propose. Our project aims to address 3 primary shortcomings with current state of the art in this particular field. The first is to build a model that is robust enough to handle a variety of input images, specifically images that are both real as well as synthetic, as you see on the left image. The second is to improve performance on counting and relationship-based questions by incorporating some graphs into a model's processing. The final area is to improve performance on outside knowledge question answering by leveraging latent information from large language models and effectively perform few short inference. So in order to achieve this, we had 3 hypotheses, and these 3 hypotheses are based on the 3 different trusts that we have divided ourselves into. So the first is there's a significant difference in performance in terms of real as well as synthetic data, and we assume that this is basically based on some appreciable statistical difference between these distributions. So our first hypothesis is that if we accurately gauge this difference and build models that can explicitly handle this difference, we'll be able to handle both real as well as synthetic images. Coming to a second thrust, when it comes to specific complex questions, such as the kind that requires counting the image or based on position, we assume that we have found out that state-of-the-art sequence generation models can help detect these answers better. Our third hypothesis is the basis for third thrust, which is given that we have the context, we have the example. If we combine this with the implicit knowledge from large language models, we should be able to achieve higher performance on knowledge-based VQA datasets while maintaining performance on other standard VQA datasets.
Thank you, Ninad. So these are essentially the intended users for what we're building. Of course, researchers in the NLP as well as the multimodal community will benefit from the work that we've done. We also hope that search engines and chatbots can both use the work that we've done to better improve their functionality. Coming to functionality, so the 3 thrusts that we have, we expect the first thrust should create a model which creates similar VQA performance on both real as well as synthetic datasets. For the second thrust, we want competitive performance on thing and spatial type of questions. And the third thrust, we expect that outside knowledge questions should also be competitively answered. Coming to our non-functional requirements, of course, all of these are important and we wanted to tackle all of them, but given the time constraints that we had, we primarily focused on the modifiability, modularity, usability, and accessibility by making sure that our code was modular. It was continuously updated in the section so that we don't any of the previous implementation. We do hope that performance, scalability, security, and reliability are addressed, and this does get deployed as an application that can be used by any. Moving on to our design considerations. So our assumptions, this was kind of covered in the hypothesis, but essentially we want to make sure that a unified state module, which is the +1 module, but the assumption is that there is a data drift between real and synthetic data, and there are models that are capable of capturing this difference. For the spatial and numerical reasoning module, the assumption is that the performance of scene graph models are actually sufficient enough to create scene graphs that will adequately supplement the forms that are given into these models. And the performance on counting object forms can indeed be increased with sufficient training on those technical terms. And for our knowledge module, it's the fact that object knowledge is indeed important, and using implicit knowledge in these latent states of the models and using that context will help in answering these object knowledge. A few of our constraints were, one, our data sets were humongous because they're both text as well as image modalities. So dealing with these image data, both of the storage as well as for our training purposes, was a challenge that we had to overcome. For our resources, again, we were heavily constrained by the computational resources that we had in the beginning of the semester. We did get access to the Babel Tech cluster later on, and that helped alleviate that issue. And these models are taking an incredible amount of time, even on these large distributed clusters. So, typically an epoch would take anywhere between 20 to 40 hours of for our finding purposes. So, that's basically the time constraint.
Thanks, Naveen. So now let's have a look at system architecture diagram. So at the right, you can see 4 modules that are representing the 4 models that we have trained. So all of those have IDFX 9 million visual language model or IDFX 9B instruct model as base. And then they have been Qlora fine-tuned on like specific data sets. So if you look at the data sets, we have Clever and VQSCP V2. These 2 data sets are being used by unified QA model for real versus synthetic images. For spatial reasoning QA, we have VQA, which has scene graphs in it, which helps to get relationships between the objects and the images. For numerical reasoning QA, we have used Tally QA, which is a specified spatial counting-based problem data set. And for knowledge QA, we have OKVQA, the outside knowledge VQA data set. So these 4 models have been fine-tuned. So now we have a unified data set, which is used to train the router model. The details about router model will be covered in the next slides, but what it does specifically is it will direct the prompt to the best, model that will answer the question the best. So once it will direct, and then we'll get the answer from the specialized fine-tuned models. So that's the gist of the system architecture.
So just a quick clarification on the diagram. Once you make a choice through the router model, then you're using the output of one of those.
Yes.
So the arrow that kind of combines things is a little misleading. It looks like you might have like a combiner at the end. It'd be perfectly fine with just that an arrow coming
Out of each other.
out.
Yeah, and this is the data flow diagram. So just from what I have explained, so this just explicitly shows us how the data goes. And yeah, at the end, the arrows are separately, one from each model.
So to be very specific, we are using the IDFX model as explained earlier by Pratik. So let's delve deeper into this model. So it was first the Flamingo model, which was proposed by DeepMind, and IDFX is the open source representation of this model. So Flamingo was trained using the cross attention between vision embedding and language input. As we can see, there are gated cross attention layers in the language model. It uses CLIP model as its backbone for image embeddings, and the Llama model for as a language model. And it's available in 80 billion and 99 billion parameter sizes, and we go forward with the 9 billion parameter size. So moving on to the router model. So over here we use the multimodal biotransformers MMBT model, and also tried some other experiments and other models. So the MMBT model, it was proposed by Facebook AI Research, and it was it's like it has ResNet 152 architecture for handling the image embeddings, and it involves joint fine-tuning of unimodally pre-trained text and image encoders, and so it in general uses early fusion techniques, and we think that this early fusion technique is the one which helps, and along with the bidirectional transformers, so it helps in better training the router model.
As for the same graph generation, a model called relational transformer is used. This was introduced in 2023. The image features are used to extract entity representations. These are then used with the image features to identify the subject and the object. These are the two entities in a triplet. The model then uses three attention mechanisms, that is coupled self-attention, decoupled visual attention, and decoupled entity attention, to identify the relationship between the subject and the object, and then generate the feature.
And then we introduced some design of our elements in our system. For the unified QA model, we fine-tune the edifix with both real and synthetic images using low-rank adapters. So the lower layer are injected in all attention layers, and it's sort of for our other design. And for the spatial reasoning module, a single graph generation is used as start, as we introduced before. We shall take the image as input and output the single graph information in triplet format. Then this information is added with prompt and sent to the edifix model for final inference. Then for the numerical reasoning module, we fine-tune the model with calculated dataset and also use the lower method. For the knowledge module, the embeddings from a small VK model or a text encoder are used by us to find the similar examples, like to do the example retrieval. The contacts are also obtained from the image, and the information is also passed with a prompt to the fine-tuned edifix to get a final answer. Finally, this is the basic design of our router model. The model is trained using our mixed datasets, which I'll talk about later. In detail, every downstream module will first be evaluated on this dataset. Then the router model will learn when each module performs better. So therefore, it can predict the appropriate module for the given image question here to get a final.
So here's a brief intro of the evaluation metric of the given data. So each source basement either having a specific set of evaluation metric, but one only evaluation metric we are all using a substring match. So substring match provides a relaxation upon exact match, since the predict answer are sometimes phrases or consisting multiple answers, while the ground truth inverse also is often ignored. So this metric converts everything to lowercase map conjectural numbers to digit, then check if the ground truth exists as a substring. And we believe this provides more relaxation for evaluating the entire model. So here is a version of our testing data set. So things we further rely on the multimodal to derive different question inputs, different question images to different specific modules. So we basically need to construct a new training set and a new testing set. So to train the model selector, we constructed a new training data set using training samples from each source. And we then construct a balanced test data set to evaluate the overall performance. And to prevent information leakage, we remove images in thrust-specific testing set that appear in other thrust training sets.
Great, on to some results. So thrust one, which is refresher, the real versus synthetic data set split. We want competitive performance on both. So first we decided to, before we did pick Idefix as a model, we also tried Lava, which is also another multimodal large language model, to see which model would make sense to fine tune. And just based before any sort of fine tuning, we saw that the performance on Clever, which is the synthetic data set, was significantly better with the Idefix model than on the Clever model. So, on the Lava model. So we decided to go ahead and fine tune the Idefix model. And we run this with and without some sort of prompt engineering. And what we did was we took Idefix and we decided, hey, Idefix has seen real images before, so we're going to give it a bunch of synthetic images to learn from, and we gave it 100% Clever data set, their trained data set, and trained it on one full epoch, and we saw that wow, the performance does go up all the way to 53.93 and 52.44% right there, on Clever, as opposed to just 46 and 47. However, we saw that the VQA performance or the real image performance dropped from 53.93 to 27.38 when we did that. So there was some sort of catastrophic forgetting happening, and we realized that we needed to actually have some sort of a mixed data set of real and synthetic images when we trained this model. So the final model that we picked was a mixture of 90% clever data set and 10%, and 10% BQA data set. And then we see that the real image performance is preserved while we see an improvement in the clever data set performance. How we came about this 90-10 split was through experimentation. We tried splitting, we tried a 50-50 split all the way to a 90-10 split, and we actually saw that the performance was fairly similar across all of these different splits. So even though the performance significantly dropped from BQA at a 100-0 split, we realized that introducing even a small amount of real images helped preserve that performance. However, when we did train this more epochs than just one, we did see the 90-10 split did go down, while 50-50 split maintained the performance. However, we see that the 50-50 split and the 90-10 split are fairly similar in performance. So we realized that doing just one epoch of a small amount of real images and a large amount of synthetic images would be fairly equivalent to multiple epochs of this 50-50 kind of split, right? It's not learning as much from synthetic images. Yeah, so looking at some real examples, let's look at the one on the right first. So the other small shiny thing that is the same shape as the tiny yellow shiny objects is what color, right? So this is a synthetically generated image, and this is a fairly complicated thing to do. You need to see what shiny is, and you need to identify the shape, and you need to find out that the yellow shiny objects will basically have two in the back, right? So we see that the yellows this cyanide cube is basically the answer to the color cyan. So it's able to infer a fairly complicated relationship. However, it's not perfect. Of course, but one of the examples where it does do bad is what number of objects are made of the same material in the gray cylinder. So the gray cylinder there is metallic, and you see that it's not 4, it's 3. So basically, we realized that some of the counting questions might be better directed through the other module, but it does do pretty well on a lot of some real image results. Again, the first question is the cutoff on the left side of the frame. The answer is no, the reaction answer is yes. So this is again something that would have benefited from a scene graph into the prompt. So that's something that would have helped in this, and maybe if it gone to class 2, that would have been better. But a simpler question: how many graph in this picture is doing pretty well in this image. Yeah. So let's do.
So coming to the results on the spatial reasoning questions using scene graphs. For findings, the subset of the GQA data set was used. This is because GQA data set is really large. It has 40 million points in train and 2 million in val, and it becomes really hard to train the model. So the relational and the balanced questions are used, and this brings down our training set to about 500K and a val set to about 150K, and this still takes 30 hours to train. This summarizes the results of the models fine-tuned with different scene graphs when tested with prompts that contain different scene graphs. So the first thing is on the unfine-tuned model, adding the ground truth scene graph improves accuracy significantly. It's almost 20%. And the upper bound of the performance is achieved when we train with the ground truth scene graph and also test with the same ground truth scene graph. This is 91%, and it's even 15% greater than fine-tuning that's in the previous row. And we can also observe that if we were to choose between fine-tuning and using good scene graphs, using good scene graphs actually gives us better performance than even fine-tuning on a specific data set. And when we don't have any scene graph during test time, we see that the model is fine-tuned without scene graph performs better. And when we have good scene graph, the model trained with the ground truth scene graph performs better. And when we have low quality scene graph, both the model which is being fine-tuned without scene graph and the model that is tuned with generated scene graph are kind of similar. It depends on the sample that we choose. In trying to understand how much the image and the scene graph modalities impact the model's performance, a zero image and a Gaussian blurred image was used with the prompt to check how much it matters. So the first thing we see is adding the image helps give consistent results across both the binary and the open-ended questions. This reduces the chance of the LLM guessing. And we also see that adding scene graph improved the performance on open-ended questions. So we know that ground truth scene graphs are better than generated scene graph. But I was trying to see if this is because the model that generates scene graph is bad or the data that it has been trained on is not exhaustive enough. So GQA has 1,700 unique classes of objects, but but the scene graph generated object detector was only trained on 150 classes. This means that objects like computer were never part of training the scene graph generation model, and they don't come up in the scene graph itself. So to evaluate this, I took a sample of generated scene graphs such that the object we need to answer the question exists in the list of the questions that scene graph was trained on. And I did this using POS tagging. And from this subset, we see that there is a slight improvement over using no scene graph when we add generated scene graph in some of the cases, that is in the first one and in the last one. But it's not conclusive, and we need to do more manual analysis is what I found. So that is that. And on closely observing some of the cases, we see that predicted answers are actually not that bad. They're equivalent answers, however, the current metrics like substring accuracy does not really catch it. This is one such case. And this is another such case where it is hidden. And this is another such case where the geometric answer is very specific. So finally, we can infer that good scene graphs make a really significant impact on the QA task and could even do better than fine tuning. The image modality helps answer the binary questions better, whereas the scene graphs help answer open-ended questions better. Technically, good scene graphs is sufficient to actually observe an improvement, but the images also provide a slight boost to the accuracy. And the scene graph generator model gives good scene graphs when the objects we're concerned about exist in a very smaller subset, but we still need to do more manual error analysis of this to figure out if it's good. But there's still a lot of scope of improvement for the scene graph generation models. And finally, the current evaluation metrics existing do not capture these cases where the models predict equivalent answers. So the scope of improvement can be training the scene graph generator on more classes, improving the general methodology of the scene graph generation, exploring methods to also leverage the graph structure in the prompt to the of the scene graphs, and also developing better metrics to evaluate the task better.
Now let's look at the results for counting, how our model performed on counting-based problem. So initially, experiments were done to see how IDFX 9 billion parameter as a base without any fine-tuning performs on the dataset. We used how many QA and tally QA datasets, but tally QA dataset came out to be a better dataset or better choice for the dataset, as it has a simple as well as complex question types. The number of questions is high, 287 questions, as well as it has 19K complex questions. So after the individual, after the base results, what was done is we fine-tuned, fine-tuned on the tally QA datasets. And you can see grain size was 246,318 questions. So when IDFX 9B instruct model was used and we fine-tuned for one epoch, we found that we got the accuracy of 51.9%. But having further fine-tuned for 5 epochs, it increased accuracy to 58.4%. And this is the model that is used in the router model at the end. Let's look at a few examples. So we get good performance on simple questions. How many people are there? 14 exactly. So and close prediction for most of the answers that we have seen. So we have a metric, mean average precision error, which gives us okay, even if the answer is how far off is the answer. So we found that it is after fine tuning that metric improved. So the answers were, even if not the exact correct answer, they were closer to the correct answer. So yeah, we give 4 as answer, correct answer was 5. Honestly, the middle one looks like oranges. So I would agree with our model. How many wheels of the skateboard are there on the ground? So even if it doesn't see the wheels, I think it predicted it really well. This is one of the complex questions, or at least reasoning questions, I would say. The predicted answer is 2. The exact answer is 3. Yeah, but there is still a scope of improvement. So I think how many beers are there? It just takes the front 3 beers and not the 5 in the background. So the actual answer is 8, but we give 3 as the answer.
Yeah, so then for the knowledge module, we mainly consider these three consequences in our experiments. First, we want to use the flowchart of the bomb. So we need to consider which example retrieval method we use. And then we consider the number of samples in our bomb. Also, if we use only pre-train it or the fine-tuned model, then we consider other prompt design such as adding context of answer candidates. So to retrieve examples, we show this example here, this table here. The simplest way is based on the question similarity. So we implement a bird-based method. Then since we are dealing with this multimodal class, it's natural to also involve the image information into the similarity calculation. Here we try to use MCDS BK model, a roughly simpler BK model, and also the edifix model itself for the embedding. And looking at the results, we can see that the three similarity-based methods have the similar performance, and they are all higher than random examples. But the takeaway here is that the larger model like edifix may not have the advantages in the example retrieval way. Like a simpler model with less embedding time could be a better choice. And also here I show the experiments with different number of examples with or without the fine-tuning model. We can see both fine-tuning or adding more examples help with the performance. However, as we add the examples, you can see the last column, the inference time will increase dramatically because the longer prompts will take the large model longer time to process. So there's a trade-off between the accuracy and cost, considering all the limitation in the real scenario.
So we also experiment with different content. So for problem design, we may consider to add context information for answer candidate in the prompt. So context information is like a higher level description of the image, like caption and trust. So it provides the model a more direct understanding of the image by transforming image figures into natural language describing what is happening inside the image. So, and the purpose of answer can be followed by reversing figure we're reading. So the top 8 answers are produced by a vanilla, like a simplified BPM model. And then we provide the answer candidate to our large language model to see whether it can improve performance. So from the above, we can see that adding context actually help increasing the performance a lot, but adding answer candidate doesn't help that much. So we believe this comes to the limitation of the vanilla BQA model we're using to produce the candidate. So that BQA model is really simple. They only have a small answer vocabulary only consisting single word answers. So if we pass that information to our large language model, it may be actually limiting its ability to produce more complicated and accurate answers. So here's the error analysis we conduct on our first result. So if you can see the picture on the left, the question is asking for what slope is pictured here. So while the correct answer is B or C slope, so our model produces mountain as a result. So this shows our model's inability to really contextualize the question in English appropriately. So this feels like for us, it feels like the need for the model to better understand and interpret what is actually being asked here and what is the image calling about. And for our second example, the question is asking for what type of process occurring here. So the correct answer should be making donut while the prediction is cook. So cook is too general answer. So it shows our model's inability to produce more precise answer with finer detail. So for our third example, the question is what animal does it mean on a piece of paper? And the correct answer is fixed while our model predicts now. So we believe this is not actually the error of our model, rather than it was an error or a limitation of the labeling in our data set, because the pepperoni was made of both beef and pig. And while the label only tells us pig, but our large language model is able to produce another correct answer. So here's a brief recap of our limitations. So we first, since we're using a smaller version of IDFX, we believe that it may not be enough to produce a highly accurate and precise answer compared to a larger one. So we may think that if we use larger instead, we may be able to achieve high performance. And our second limitation comes to lies into our evaluation. Because right now we're still depending on action-based evaluation. So the answers with very different wording, but essentially similar or exact meanings may be curious. And we feel like the third limitation actually comes from opposite-based answer labels. So it may have limited representation of generalized answers, And we can also predict like bias toward particular perspectives.
Okay, so moving on to our router results. Before that, we need to first understand a few heuristics which we have used. So now we have a test data with us combined, which has combined all data sets in it, and we have ground truth results for each and every model using it. But now we still do not have the exact labels where the router model should route the to which model should it route the input image question pair. We could either use multi-label, but performance of multi-label is not that great. So we went for multi-class, and before that we had to like assign the labels to particular models. In that, so first heuristic which we used was if only one model is predicting the image question pair answer correctly, just assign that label to for that image question pair. Otherwise, label image question pair to the original model from which it to the original model for which it was primarily trained for. But the problem with this heuristic was that there were examples where, such as clever data, for example, any data for that sake. If it was not correctly predicted by its primary model, but it was predicted correctly by another different models, it was still assigned to its primary model, which should not have been in the case. So we went on to the second heuristic, where the case one remains the same, but if now the label is there are multiple models predicting or not a single model predicting the answer correctly. So we take the that model which has the highest performance on that overall data set. But now the problem with this was that it was extremely difficult to train the router model because it could not find any patterns as such in the data. So we went on to the third heuristic, where we followed the heuristic one except for VQA CPV2 data. But because VQA CPV2 data, it's the real data, and it basically could be predicted by any of the other models of trust 2 and trust 3 as well. It does not require specific trust 1 model only. And so basically for VQA CPV2, we follow the heuristic 2. Moving on to the results of our router model. So we can see that heuristic 3, where we use classification, it gave the best performance overall. And even further subsequently when training the on the overall system, it was the one which could give the best performance. Over here, we also tried Breach Tower model along with MMPT, but MMPT, we can see that it has performed fairly better than the Breach Tower model. And here are our results overall. So we can see that for the every specific data set which we had in our combined data set, it has a kind of a similar accuracy. And for the overall system, we reached around 55.2% accuracy, and the baseline non-fine-tuned IDFX model, we also calculated its accuracy on the test data, and it was about 15.8%. So we can see we can go about 4 to 5% of those by using this entire router model method.
Okay, now moving on to learnings. So in terms of learning throughout the semester, being part of this team really helped us achieve both technical as well as non-technical aspects. So we learned how to do LLM training, both using quantized manner as well as with distributed training. We learned how a mixture of experts can help achieve better results. We learned how to better use scene graph along with prompt engineering, and also worked on data set creation. In a non-technical area, in the team of 7, we did have challenges and in terms of initial hiccups with respect to project management. But as the semester progressed, we were better able to utilize everybody's talent and manage to achieve our goals accordingly. We also collaborated a lot with team members, especially during the design of our router models, where all the trusts were involved with providing data and designing the models. We also had a lot of collaboration within the trust as well for cases like using the Babel cluster, understanding how the system works. So our project was very dynamic, and a lot of fine-tuning with hyperparameter was done. And this was iterative, so we learned what iterative progress is. To conclude, this semester we achieved building a robust multimodal question answering pipeline with 4 expert models that deal with real and synthetic images, and benefit with respect to spatial and numerical reasoning questions, along with implicit knowledge from large language models. We also help tie the 4 models all together to an entire pipeline by introducing a router model that routes the input to the corresponding output, thus benefiting from advantages of each fine-tuned model. In terms of future work, we want to try hosting this as an HTTP endpoint and introduce other SOTA model, state-of-the-art models with additional modalities. So this is how we think we should deploy the model, where we containerize each model into containers web servers. We want to post the data in S3 so that the data transfer is simple, and then it's just going to be an API request from the user. So yeah, these are a few references that we use for, and we have cited this in our presentation. A few terminologies for people to get benefited. And we did few changes to the previous documents because since it was an iterative process, we had to keep changing the diagrams.
So first of all, just let me say that I really appreciated how well coordinated and cohesive the final presentation was. We did a lot of work to show a lot of results and a lot of thinking and a lot of ground that you covered. And I just wrote here in my notes that if you were presenting this in 11,797, you'd be getting an A+ for the amount of work that you did there. I do have a few things that could be tuned up. I think that there were a few things that weren't clear until we got deeper in the presentation. So I learned finally that knowledge really means retrieval augmented, extraction of candidate answers in contexts. And I also learned that you were verbalizing things into the prompt architecture. And maybe it's because we didn't spend enough time on that early diagram where you had the full features and everything flowing in the model. So if you're going to write a paper and submit this, you definitely want to be very clear about, sort of sure it's knowledge that's getting verbalized and put into a prompt. And we probably want some data flow diagrams that actually show sort of what the prompting is in different conditions. But this is not really a big deal at all. I think it's something we can easily add. It also wasn't clear in the beginning with the external knowledge sources that you were using, because when you say that, it sounds like exogenous knowledge or Wikipedia or something. And the fact that you were doing retrieval augmented prompt engineering, you should probably just say that instead of knowledge. Knowledge is probably the most overloaded term in AI, so you want to be careful when you use that. The explanation of the scene graph results was really good. And I was wondering whether you considered ablating the scene graph as well as ablating the image fidelity. So it's a very common thing that when you're using a graph representation, you want to find out how sensitive the model is to maybe deleting an edge, deleting a node, changing a label on an edge, and changing a label on a node. So that might be something to think about. Although I think probably the challenge now is that it's not even close enough to being good enough. You don't want to ablate it too much. But I think people will want to know, for example, if you just do a tiny amount of ablation, there is the whole advantage there and drop off. Let's see. And then, I think you did verbalize the graphs in prompt engineering, and that was implied, but I didn't quite get it from the data flow diagram. So you want to make sure that you make that clear, and that you're not doing graph embedded layers in your model or something like that. So can we go back to the pepperoni slide? So I think this is really interesting because there's absolutely nothing wrong with saying mountain in the first case. If I had been trained on lots of sports and skiing and so on, okay, I'd be disappointed. But if all of it is like outdoor scenes and none of them have any labels that have anything to do with sports, this is the best you can do. And in fact, mountain is a more general answer. Okay, so this is, and that was one thing I liked about your presentation, is you showed how the errors are not necessarily wacky errors or hallucinations, but they're close. And they're the kinds of things that we would expect from the system is really learning on what's going on in the domain. The second one I think is great. What type of process is occurring here? It's cooking rather than cleaning or manufacturing or something. So cook is actually the right answer. If we ask what type of food is being prepared here, then cook would obviously be a system that doesn't even know about food. Okay, so sure, the answer is too general, but I would actually claim here, what if I presented this in the paper, that the level of generality of the answer actually matches the level of generality of the question. Okay, and I think that's an important way you guys should be describing sort of the shortcomings of the data set. Because when you have something like this that can actually learn, now it's literally learning a more general answer, which might be more appropriate than the generality of the question. And I think also the last one's fine. I think that you know, if the system came back and you said, why do you think it's cow, and could actually tell you that I identified this as pepperoni. I know that pepperoni is sometimes, you know, made of cows or whatever, that would be good. Here's one where I think you'd have to start being able to give more of an explanation of the answer, because it kind of does look like just a wrong answer. But I agree with you that there are, you know, pepperonis that are made from cows, so we would want to, you know, basically have a little bit of an explanation there. So the last question, and then we got to move on to the next theme, is how does this really compare to the state of the art? So you get about 4 to 5% over the sort of non-fine-tuned edifix. Is that really sort of the state of the art for these tasks right now, or is there something better?
So the thing is, for specific data sets, there are models which have been trained, for example, on the real synthetic, on the synthetic data set. They've posed it as a classification problem because the answers are all either like 1 through 10 or just a few colors or a few textures. So those do really well. So this doesn't come close to that.
So really another thing we should be claiming here is that you're the first team to try to do this on all of these data sets at once, exploring all of these very important techniques. Okay, so there's a very important architectural hypothesis here. And since that's the way we do business at CMU, you sort of assume that. But now if you're going to write this as a paper, that's going to become a really fundamental thing, where you're saying we got to stop over-tuning models to specific data sets and formulations of the problem and consider doing things like this. Then if you take edifix as a strong baseline for doing this, and then show that attending to those elements of the architecture allows you to go beyond, then you might have a publishable result. So you should definitely spend some time talking about this. Thanks, Pat. Great job.